So let's start the first session of today. The first talk will be Aina Palau on the talk of the role of magnetic fields in the formation of stellar clusters. And Aina, you will receive a message 2 minutes before the finish of the talk. As a reminder. Okay, so let's go ahead.
Okay, good morning everyone. Can you hear me?
Yes.
Okay, so good morning everyone. I would like to thank a lot the organizing committee and in particular the local organizing committee who is setting up everything, also for the remote connection. Thank you very much. I'm very happy to see Paul here, so full of energy and very enthusiastic as I always seen him. I'm very happy to see this because I didn't see him since about 20 years, I think. So I'm very happy to be part of this celebration. And I decided to talk about this, I would like also to be in Taipei in person. This was not possible, but I hope to do so very soon and say these words in person as soon as possible. So I would like to talk about this topic because it was a relatively recent paper, but it was also a work involving all these collaborators, and in particular, these highlighted here in red were highly involved also in my PhD work, where of course Paul was crucial to this. So that's why I would like to give you that context. I did regular stays at the CFA to do my PhD thesis under the supervision of Roberto Scalera and Paul Hall. I did these stays from 2002 to 2005. And Maite Beltran was finishing her PhD at the CFA at that time. Susan Miguel Girard had finished his postdoc at Lima and was back to Barcelona. And Luis Zapata was doing his PhD thesis at the CFA, and I met him there. So at that time, at the beginning of this period, Paul was, let's say, so to speak, easily available. And to me that was really crucial because he gave me great advices to start and to define my PhD topic. He told me, take the staff directory of the CFA and knock on its door and see what you would like to do in your PhD thesis. So I met and I had very interesting conversations with all these people and many other people that I talked here, but in particular, the top hunter conversation was to me very important. He told me, I would really like to understand how massive clumps split up into denser and more complex structures and to understand if this behaves differently from different environments and how this works. And I found this topic very fascinating, and that's why I started to work on this fragmentation stuff. So, of course, the next step was to do many proposals as many as possible. Most of them were rejected, but some of them were accepted in the end, and that's how the thesis started. But later Paul was traveling fortnightly from Boston to Taipei. That was really a very frequent travel schedule, and well, Chizu here helped a lot. But among the students who were also wondering how will we have feedback from Paul, or will we won't receive so many advices from him because he's traveling so much. But I was really surprised to see that feedback from Paul arrived from everywhere. Every possible means in the earth were used. And of course email, but also FedEx. I was once in Barcelona and arrived a FedEx package for me. I didn't know what it was. And luckily it was the correction they made by Paul on one of my papers. And also with a note in a corner saying somewhere over the ocean. So yeah, this was really stimulating for me to see that my advisor was doing everything possible to really give this feedback, and it was really very useful. So also some crucial events that I could cover that, like Paul saying, I read your paper on the plane, or giving very wise advices like, don't wait, move ahead as quickly as you can. These kind of things were really important to push and to follow a definite way and not to get too lost in so many things. So that was really useful. And then I already got data for 3 regions, but Paul said you need, to complete your PhD thesis, you need 1 region more. And I was thinking, okay, I don't know what else I could do. But Paul said, I'm thinking about 1 data set that you could use, but first we need to meet Chisu. And we went to Chisu's office, and Paul asked him about which data set could I use. And Chisu said, okay, I could use AJ211. And Paul said, that's the same one I was thinking, but I didn't want to tell you before. So I thought that was a very wise way to proceed, because as a leader, maybe you should just go ahead and not double check with anyone, but Paul was double checking and to be sure that things were the best. So that was very wise lessons to me as well. So going back to the fragmentation stuff, what I wanted to study was trying to understand why some molecular clouds fragment very efficiently while others not. And to understand this, we need to understand the process where a molecular cloud, which is, we know now it's filamentary, starts to form substructure, and at some point these substructures of the cloud gets gravitationally stable, and in the end a cluster is formed. So this first step of fragmentation is the one that we wanted to understand. And there are many agents that can control fragmentation, obviously thermal pressure and density, as given by the Jeans criterion, but also turbulence, also the angular momentum, and also the magnetic field. And our goal was trying to understand if any of these agents is controlling or dominating the fragmentation process. For this, we need to build a sample, a statistically significant sample, and we started to do this in the PhD based on the samples at the time, Sergio Molinari, Henry Boyd, and so on. And in the PhD work, I just ended up with 5 regions that were observed in different interferometers, and it was a completely inhomogeneous sample, so I could do nothing with this apart from studying each target individually. So later on, we got more data with the plateau reviewer, and we could start with a more uniform sample, and we could start to study some of these agents that I showed here. For example, the fragmentation level against the non-thermal oxide dispersion, or the fragmentation level against the rotational to gravitational energy, and it seemed that there was not any clear trend for these parameters. So we proceeded studying the magnetic field and density agents. So for this, we used the legacy program of CHISA and selected very specific regions so that we could build, again, a very uniform sample with very similar distances and so on. And we measured the fragmentation level with the most extended configurations of the SMA for each region, and the magnetic field with the subcompact and compact configurations. And of course, we wanted to measure the magnetic field strength, and for this we used the Davis Chandler-Sekar method, as many of you know, which assumes that there's a left scaling component of the magnetic field and a perturbed component of the magnetic field. So to estimate the magnetic field strength, we need to know the density, the velocity dispersion, and the dispersion of polarization position. So for the density, we use gradient intensity profiles and SDs. And for the loss dispersions, we use the X13 CO plus line that we have in our data sets through the spectrum and measure the line widths. And for the polarization, position, and dispersion, we use 4 different approximations. One of them being the standard deviation, another one fitting Gaussians to histograms, another one calculating the structure function, which naturally separates dispersion at small scales from the dispersion at large scales, and the method from Martin Code in 2009. So we end up with 4 different measurements of polarization, position, and dispersion, which corresponds to four measurements of magnetic field strength and 4 measurements of mass to magnetic flux ratio. And by plotting these, the chromatography level against all these quantities measured in different methods, we found no correlation at all. So we went back trying to understand how were we measuring magnetic field strength, and thought that maybe the velocity field treated similarly to the magnetic field. So this means that we should have separators of the velocity field in the small scale component and a large scale component. So we did this for the structural function the same way that we had done for the dispersion of polarization position angles. We did exactly the same for the velocity, also the velocity field. And when we did this, we found a tentative possible strength of fragmentation level against mass to flux ratio as predicted by the numerical and theoretical works. So we think we should study this in more detail using ALMA data and try to see if this is confirmed or not. So we were completing all these things. We only were missing the density, and in our data set we also could calculate the density of the radical core, and we also found a more strong relation. So this work should be followed up with ALMA data, of course, and that's what we are doing now. And I just would like to say, before finishing, that Paul was worried not only about science, but also about each person behind that science. And I'm saying this because he used to ask me more than 10 years ago he was worried about already gender violence and gender balance. And he used to ask me if I had felt at some point any proper comment or things like that. And I think more than 10 years ago, this was not the usual topic, and he was really he had a lot of vision at that time. And I think that he combined a high scientific quality with a high human moral, and this made an extraordinary of productive projects and very successful projects. So I'm very proud to have had Paul as a supervisor, and thanks everyone, thanks Paul, thank you very much.
Okay.
Yes. Can you hear me?
Now? Yes.
Okay, so
Yes.
yeah, we don't have much time, so one question. Yes.
Maybe now there's a little bit on. Now that's what it sounds like.
Now? Yes.
Okay, so one question.
Okay, yeah, I gotta ask. Aina, very nice talk. So I was just wondering, those coordinates you are showing, mostly proto-stellar, I mean, proto-star, or something, not stellar, pre-stellar. Can you hear me?
I didn't catch it very well.
Maybe I need to go
Yes. So can you repeat again?
I'm wondering whether those fragments that she found, observations, more associated with the Proto-Star mostly, or including a pre-scalar.
Hello. Can you hear me? Hello.
But it's hard. Giselle, can maybe you
Yeah, Chair, to repeat the question.
Yes, so, okay, but I need, okay. Yes. Nakayoshi, question, can you hear me well now? Yes. So the question is about whether these fragmentation are associated with protostars or not. Can you check that?
Yeah. That's an excellent question. We are checking these. In some cases, there are clear signposts of activity of star formation. In other cases, they're not. What we know is that they are very compact subcondensations. And we have done this year, we have published a work where we have revisited the genes criterion, but taking into account that these subcondensations are embedded in large-scale envelopes or clumps, and that there could be tidal effects affecting the effective genes mass. So we have revisited this in this last paper, and we found that most of them are gravitationally unstable.
Okay. Thank you very much, Aina. So let's move to the next. Let's move to the next speaker, Joan, Najita. She's going to talk about the immigration history of Andromeda or nearby galactic neighborhood. So, could you set up the? Oh, she's good. Okay.
Thank you. I wanted to thank all the organizers for putting together such a fantastic event and for the opportunity to join in remotely. Thank you so much. And thank you, Aina, for your wonderful comments, which reminded me of all the things that I love about Paul. I wanted to start also by thanking Paul for many things, but in particular for supporting me at a difficult time, all the difficult times when I was an undergraduate and a postdoc, and also to thank you for some important life lessons, not least of which are the importance of taking risks and not getting boxed in by the status quo. So today I wanted to share some results from a project that began basically from that same philosophy. So about 25 years ago, when I left the CFA and moved to the National Observatory in the US, it was time for the 2000 Decadal Survey. And our director asked us, what should we be proposing for the benefit of US astronomers? And so being a young person, not knowing anything better, my colleagues and I said, well, with all this wide field imaging that people are doing, wouldn't it be amazing to be able to make it as easy to get a spectrum of an object as it is to take an image? And so we proposed a standalone wide field spectroscopic telescope. Many people thought this was a dumb idea because did we already have enough spectrum? And maybe it was the end of survey science had already arrived. But we were pretty sure that that wasn't right. And following Paul's footsteps of not accepting the status quo, we kept on with our proposals. We made many versions of this proposal, eventually culminating in an opportunity to build a wide field spectroscopic experiment, highly multiplexed, on our own 4-meter Kitt-Peak telescope, MAOP. This was the Dark Energy Spectroscopic Instrument, or DESI, which saw first light about 3 years ago. So I wanted to share a little bit about what this instrument is and one science result. So in order to build DESI, we had to change the top end of the instrument, the telescope, to accommodate a prime focus fiber spectrograph that has a 3-degree diameter field of view that's populated by 5,000 robotic fibers, robotically positioned fibers. The light from the fibers goes down a 50 meters of fiber optic cable shown in purple, meaning where they feed a bank of 10 3-armed spectrographs that together cover the wavelength region from 360 nanometers to 980 nanometers at monospectral resolution. This is an amazingly efficient system. After you observe 5,000 spectra, within 2 minutes, you're ready, you've repositioned and are ready to go again. And so in one night, it's possible to get spectra of 60,000 to 100,000 objects. It's a very stable instrument. It's on the telescope every night, all the time, and it comes with a fantastic data reduction pipeline that produces redshifts by breakfast. So you observe at night, and in the morning, the data is used so you can see what you've observed. With this efficient system, so far we've measured 26 million spectra, 26 million galaxies and quasars, and spectra of 9 million stars. And the first data release occurred earlier this year. But I wanted to share just one science result that's come out so far. And that has to do with the origin of galaxies. When we look at pictures of galaxies like this, they seem pristine and eternal, like they've been there forever. But not really. We know that galaxies evolve and actually assemble. They build up their stellar populations, much in the way that countries build up their populations. With some of the inhabitants, stars in this case, born in the galaxy, and others arriving to the galaxy in waves of immigration, much like the history of a country like the United States. So, for example, for the United States, back in the late 1800s, we had a wave of immigration from Europe. And several decades later, another wave of immigration from further east. We've also had waves of immigration from the north and from the south, and all these flows together have built up the population of a country. We see a similar thing going on in our own galaxy, the Milky Way, where if we look at the energies and angular momenta of stars in the halo, we see that the distribution is clumpy. And that's interpreted as evidence for individual galactic immigration events. Now, it's hard to see, when you look at a plot like this, you may not believe that story. And partly that's because it's hard to see what's going on in the Milky Way because we are in the galaxy. And it's hard to look around and figure out exactly what's going on. It's actually potentially easier to look at a galaxy outside ours and see what the story is. And so that led us to think about looking at the Andromeda galaxy, our nearest neighbor. When we look at a normal optical picture, it looks so perfect and normal, but if we look at very faint star number counts, you can see that there are some odd things going on. There's a shelf of stars here, a shelf of stars here, and a big stream, which has been interpreted as evidence of a galactic immigration event. Is that really what's going on? And can we learn anything from spectroscopy? So this is what we tried to do with the DESI instrument, and we were lucky enough to be able to study 3 fields with DESI, and shown here with these strokes. And in under a little less than 4 hours, we were able to measure 11,000 velocities, which are shown here. And so you can see that on the disk of the galaxy, you can see the rotation of the disk. But away from the disk, there are many stars with high velocities and something interesting going on. What is it? Well, we can learn a little bit about that by looking at sectors of the galaxy and plotting for each sector the velocity of the stars as a function of the distance from the center of the galaxy. And when we do that, we see that it's not a random pattern. The stars arrange themselves into these delicate, intricate structures, like these streams here, and another parallel stream here. There's a kind of attractive feature here. And if we go to this other sector, sector 2, you can see that there are nested wedges. There's one triangle here, and another triangle here. And if we went through all the sectors, we'd see similar kinds of features. And when we look at all the features together, in velocity and galactocentric distance, the structure is basically of nested chevrons and a stream. These are the footprints of the galactic immigration event that was predicted by theory, but never seen so clearly before. What is that prediction? Well, if we look at this old simulation from 1988, you can see that when there's a target galaxy and a small galaxy falls into it, it's at first stretched out as it passes through the galactic center, and then splashes on one side of the potential and oscillates back and forth, creating these shells. In velocity, the companion comes in, goes to high velocity, comes back out, and oscillates back and forth in the potential, producing these chevrons and a streak beam. So similar to what we've seen with M31, but slightly different because this is for a perfectly radial merger, whereas in M31 it's not quite perfect. So here the stars come in, and instead of, they slightly miss the center, so they wrap around this way, and there's a shell on one side here, a shell on one side here, and a shell here, and in velocity space, we see the same sort of chevron kind of pattern. So very similar to what's actually seen in M31. So here's our simulation of the star counts, which look a lot like what the galaxy looks like, and the velocity structure, which is now what we've actually seen with DESI. So clear kinematic evidence here for a galactic immigration event. And the fact that the simulation and the observations agree so well suggests that what we're looking at here, the M31 halo, is dominated by a single galactic immigration event. Now, if you work really hard, and if you're a black belt astronomer, you can actually see this sort of data, this sort of signature in our own galaxy. So in this nice paper here by Proto-Star, they, through a lot of data processing and a lot of careful work, they were able to pull out these chevron signatures in the Milky Way. This is really hard work because we're inside the Milky Way. If we look outside the Milky Way and you couple that fantastic view with an instrument like DESI, which makes it as easy to take a spectrum of an object as it is to take an image, it's possible to see this really directly, and even someone who doesn't really know anything about galaxies can also make a discovery. So it's pretty interesting here that both the Milky Way and Andromeda have these sort of chevron structures indicating that they're dominated by a single immigration event. One occurred 8 to 10 gigayears ago in the case of the Milky Way, and one only a few gigayears ago in the case of Andromeda, suggesting that these two galaxies, so close together, have had a similar history, and perhaps Andromeda gives us a glimpse into our past, what our own galaxy looked like many gigayears ago. Either way, it's amazing that we can see history laid out before us, the footprints of immigrating stars recorded in their motions that we can still see today. And so just to summarize, I hope I was able to share some of the fun of the DESI instrument, how that when it's easy to take a spectrum of an object as it is to take a picture, even inexperienced people can make discoveries. And although DESI was designed to probe the mysteries of the universe, dark energy and dark matter, it's also slowly revolutionizing our ability to study the mysteries of galaxies. And in this case, perhaps open windows onto our own past. I hope the story also illustrates how telescopes can have very long lives. The Yale telescope that DESI is on is 50 years old this year, and despite that, it's not done yet, it's off on a new mission. And just to put that in context, just a few hours of observations with DESI were able to supersede many decades of work with Keck and other large telescopes. So with that observation, that even after 50 years of hard work, you can move on to something new and still be at the top of your game, I'd like to thank Paul again for all his teaching, mentoring, advice, and friendship, and wish him all the best on the next phase of his career. Thank you.
Thank you very much, Joan. Any questions?
I have a question. Joan, can you hear me? She may need to have it.
Yeah.
Okay, good. So I see the stream coming in and I see the chevrons, but you want to associate the stream and the chevrons with a single event. Is that because of the spacing of the chevrons suggests that you're seeing this oscillation and not other previous events that are also oscillating?
Yeah, I think the fact that if you can make a model that reproduces a lot of the morphology and a lot of the detailed kinematics of what we see in the halo, suggests that the stars that we observed can all have come from a particular immigration event. We didn't study all the stars in the halo, and so there could be other events that have also occurred, but they may not be the dominant ones because most of the structure that we see can be interpreted in this simple way. So taking it as Occam's razor, it's consistent certainly with most of the structure in the halo being dominated by a single event.
Excellent.
Does that make sense?
Yeah, thank you.
Any other question? Problem with the microphone here.
Okay, so thank you again, John. And let's move now to the next speaker, Alison Coil. And she's going to talk about ionized gas in a hot radio cell.
Sorry, it's not liking the sharing my screen. 1 second. I think I have to leave and come right back. It's going to take like 30 seconds. Sorry.
Yeah, okay, well. So of course, as a family of Poles, several people here yesterday we went to the internet farm. So, okay, so is she trying to reconnect again? Yes. So it's ready. Oh, she's still there. Alison? Okay.
I'm back. Sorry, it made me quit and come back to be able to share my screen. My apologies. This should work now. There we go. Okay. Okay. I think you can see it. Is that working? Okay. Well, I want to, like Joan said, thank you so much for allowing us to participate remotely so that we can be here with you all. Oh, you're using my entire screen, aren't you? Are you seeing my whole screen?
Yeah, we can see.
Yeah. That's okay. There we go. That's what it is. Okay. So I'm going to talk about a little small project that I've been working on for the last year or so. It's been really fun. It's on extended ionized gas in an odd radio circle. And so I'm talking to people from San Diego. We have a brand new astronomy astrophysics department here that we are creating for scratch right now. Super exciting. I guess to be the first chair of the department, which is always exciting. But it's interesting. Okay, so odd radio circles. So in 2021, a brand new class of extragalactic objects was discovered, which is rare. So they're called quarks, or odd radio circles. These are large rings of low surface brightness radio continuum emission. They're about 1 arc-minute across on the sky, which is huge. They were discovered in ASIAA, which is the Australian SKA Pathfinder, and then in archival GMRT data, another one was discovered. There's only a handful of these known, less than 10. And a lot of them have photometrically detected galaxies at their centers that have photometric redshifts of around redshift of a half. At that redshift, that 1 arc-minute on the sky corresponds to a defined diameter of this radio emission of hundreds of kiloparsecs. Okay, so that's why they're called odd radio circles. What are these? This is the discovery paper. So this is showing the first three on the left, and then this is another one discovering later ASIAA data. So you can see these large rings of radio emission. And like I said, many have galaxies at their centers that are red, so old, maybe dusty. And this circular structure implies that energetic events caused them. In the papers that discovered them, there was like this whole plethora of ideas around what these could be. From a supernova remnant, to a planetary nebula, to a galactic wind termination shock, to a bent-tailed radio galaxy, which we don't even really know what that is, to a double-lobe radio galaxy seen phase on, to maybe like lensing. There was lots of ideas around what these could be, but it was very unclear what was happening. So then there was another paper in 2022, follow-up NOIRLab data on the first work that was discovered called Work 1, with this beautiful image right here. So the optical is the nearby galaxies, and then the green is the radio continuum emission. And so at higher resolution, it resolved into this really interesting structure, which like maybe overlapping rings, or maybe there's arcs. In the paper, they were trying to talk about what this could be in terms of the geometry. The radio continuum data suggests that it's age synchrotron emission, and the polarization data is consistent with it being an expanding spherical shell. In this paper, they compared this radio data with this starburst-driven wind model by Katsalukis, which is an analytical model for how starburst-driven winds can populate the circumgalactic medium, and they were trying to say that maybe these could be shocks from a starburst wind from a massive galaxy, mass greater than 10 to the 10, and very high star formation rate, greater than 300 solar masses per year. This image is the image that was really intriguing to my collaborators and I, because we have been studying massive starburst galaxies that are driving really fast winds to that are into their circumgalactic media. And so we were thinking maybe these orbs are related, and it's like a later stage of the same or similar kind of thing. So I took 20 minutes of tech time, but I happened to study the galactic winds that I was studying these massive starburst winds, and I looked at the one work that can be seen from Keck. The works were discovered in Australia, you can't see them from Keck, but the one that's from our tidal GMRT is in the north. So this is a 20-minute Keck spectrum of the center of work 4, and this is a spatially integrated spectrum. This might look really boring to you. I was super excited when I saw this because there's multiple emission lines, so we can see weak magnesium 2 and neon 3, which are weak, and then really strong oxygen 2. And then we have a spectroscopic redshift of 0.45. So with that, we can fit the spectral energy distribution of the central galaxy, and we find that the central galaxy is very massive and very old. So the mass is 10 to the 11.3 solar masses, and the age is 6, about plus or minus 1 to 2 gigayears. In a starburst model, where that's what the galaxy could have had in the burst of star formation, that burst had to shut off around 1 gigayear ago. So there could have been a burst, but it was roughly a gigayear ago that ended. And we allowed there an AGN contribution and found that the AGN contribution to the optical infrared is only 3%, so really minimal. So here's the case study data. So this is Keck Cosmic Web Imager, IRyA data. So in the upper left, this is an optical image, and then this is showing the red galaxy in the center. This is the case study field of view. If we look at just the center, this is the stellar continuum, so that's the galaxies. In the lower left, this is the oxygen 2 surface brightness map. So we see really extended oxygen 2. You can see oxygen 2 in massive galaxies, but it tends to be spatially very small. So this is really large, physically extended oxygen 2 nebula in this massive galaxy. And in the lower right, this is the oxygen 2 equivalent width, which is the ratio of the amount of oxygen 2 emission to the stellar continuum. And this, again, this looks really boring. The thing that's interesting here is what the numbers are. So the scale bar goes from 0 up to 80 angstroms. Equivalent widths of oxygen 2 are usually like a few, like 2 or 3, maybe 5. So this is like an order of magnitude, too much oxygen 2 for an early type galaxy. So this is showing, this is quantifying this more. This is the surface brightness radial profile. So the surface brightness as a function of radius. This is 10 kiloparsecs, 20 kiloparsecs of the stars, the oxygen 2, and then the seeing disk. So the oxygen 2 is not as extended as the stars, but it's very extended. It goes to a radius of over 20 kiloparsecs. Again, most massive galaxies, oxygen 2 has a radius that's an order of magnitude similar to that. And then on the right, this is the oxygen equivalent width as a function, again, of radius, but relative to the effective radius of the galaxies. And this is our oxygen 2 in this Star 4 galaxy, and these are other massive galaxies that have oxygen 2. So you can see both in terms of the y-axis and the x-axis, this is a really extreme O2 nebula. There's loads of oxygen 2 and it's really physically extended. Because it's an integral field spectrum, we have spectrum kinetics at every sectional. So the upper left is showing you the centroid, the velocity centroid, how fast the gas is moving. So you can see that there's this general gradient. The bottom is just a cut through the north-south center here. So it shows this asymmetric velocity gradient from about minus 30 kilometers per second to about 100 plus 150. And then the right is the velocity width, or sigma, and it's really high. So again, here, this is a trip through the center. It goes up to about 180 kilometers per second, which is pretty elevated. Okay, so at this point, I had done all this analysis, and I was like, I don't know what I'm looking at. What is all of this oxygen 2 in this galaxy? Where did this come from? It's not normal gas in the galaxy. It's not the ISM. There's way too much O2, and it's far too extended compared to ISM or normal massive galaxies of similar mass. So we didn't think that was it. So then we thought, well, maybe it's AGN. In the radio image of this, or there's the right ring, and then there is a pulse source at the center. That's probably a radio AGN. But if you look at the luminosity of oxygen 2 relative to the radio continuum compared to other AGN, or 4 is at the very top here. So basically, there's far too much O2 compared to the radio for it to likely be due to the AGN. Also, the SCD doesn't support that the AGN is contributing in the optical. So we didn't think that was it. We also got a Gemini GMOS long slit spectrum. So KCWI is just the blue arm, so it's for blue wavelengths. We don't have the red lines. But with GMOS, we can get a long slit spectrum with the red lines. It's not spatially resolved, but we can get line ratios, and the line ratios are linear-like. So that's pointing to Fox. Okay, so at that point, all right, we have a ton of shock to oxygen in this galaxy. Great. What is it from? So at that point, I had to break the fears because I did not know what this was. So Cassie Logus had written this paper with this analytic model of starburst-driven winds. That paper was referenced in the earlier work papers that maybe that's what this was. So I contacted her, and she's at a postdoc, she's a whole fellow at Harvard, she was at Space Telescope at the time. And she ran a suite of hydro simulations, MHD simulations, of an outflowing galactic wind leaving a galaxy moving into the circumgalactic medium around it, trying to replicate both this large-scale radio ring and then the smaller-scale oxygen 2. Okay, so this is our best simulation. Let me see if I can make this work. Yeah, for some reason, nobody does the right one. Okay, on the right is temperature. The yellow is very hot gas, 10 to the 7. The black is cold gas, around 10 to the 4. So I'll run this again. So basically, what happens here, there's a wind that runs for 200 million years, and then when it shuts off, the forward shock keeps moving out, but there's a reverse shock behind it, and the gas that's interior to the reverse shock falls back towards the galaxy and cools. So if I can get one up. Okay, so this is the radial velocity relative to the galaxy. The galaxy's in the lower left there. So gas is moving out. Once the wind shuts off, that forward shock keeps moving forward, but then the reverse shock, there's a reverse shock behind it that makes gas fall back. As that gas falls back onto the galaxy, it mixes with the other gas and produces a lot of shocks. So in this model, this wind is launched with a velocity of 450 kilometers per second, a mass output rate of 200 kilometers per year, and then runs for 200 million years. This is just showing, again, the same thing, 3 stills at 3 different times. So while the wind is still going, there's this forward shock and reverse shock right behind it. After the wind shuts off, the forward shock keeps moving out to scales of hundreds of kiloparsecs, and then this inner gas that's in the shock falls back towards the galaxy at smaller scales. So in the simulation, at 750 million years, we can reproduce the scale of the large-scale synchrotron emission from the radio, and then the smaller-scale cold shock gas near the galaxy. So we think the same event caused both this large-scale radio ring and the smaller-scale oxygen 2 emission. So a starburst or could have been EGN-driven wind drives this forward shock out of the galaxy. Once the wind shuts off, the shocked wind from the reverse shock falls back towards the galaxy as the forward shock continues moving outward to underground again. So basically what's happening near the galaxy is the shock wind expands to fill this underpressurized region, and it creates this turbulent energetic medium with additional shocks as the gas interacts with gas in and around the galaxy. So the features of this wind model are generic in terms of the energy and mass injection and without regard to the source of the injection, so it could be EGN or starburst driven wind. But in order to match the observed oxygen 2 that we see, you need a high mass outflow rate, about 200 kilomasses per year, and the surface medium has to be lower than average density, otherwise that forward shock stalls. So the simulation shows that a single wind, such as a strong starburst, can launch a wind that simultaneously reproduces both the large-scale radio ring emission and the smaller-scale oxygen 2 emission when observed about a year after the event. So in case you're thinking, yeah, but how common are these kinds of winds? These are the galaxies we've been studying, are these compact starbursts at intermediate redshifts, and they have high star masses, same as the Work-4 galaxy. They have really high star formation rate surface densities that are driving extreme winds, 2,000 kilometers per second. And they don't have EGM, these are starburst-driven winds, and they have very high mass outflow rates, 200 solar masses per year. So we think that Orcs may be a later stage of a similar phenomenon. We need an extreme starburst, but these kinds of galaxies do exist. Okay, so huge thank you to Paul, as others have said. I would not have pursued astronomy as a career without your support. So I am in the field because of you. So thank you. Thanks for being my conclusion of it.
Just avoid that saying 3 seconds.
No?
Switch it on, wait for 2 seconds.
Okay, so, yeah.
Okay, so now yes. So questions, so Paul?
Yeah, just to make a comment, really glad to see Aina and Joan and Alison. Haven't seen them in years, and it's great to see that you guys are doing such exciting stuff across the entire spectrum of the things that we could possibly do, right? Especially want to know that Aina is up in the very middle of the night from the time shift from here, right? But these guys are working really exciting stuff that has ramifications. Actually, just this latest one from Alison, I think we have to look at our own galaxies and various features and think again about the potential of the bubbles that we see and the reverse shock that may be present that we haven't paid attention to. So this must be a common phenomenon in many cases, right, Alison? You think? You might have to repeat that.
Yes, so,
Paul is asking whether this is like this phenomenon should be like quite common in galaxies.
Yeah, so I think the question is, like, why don't we see these more? Is it really common? Is that the question?
yes.
Okay, so I think
All the sources, yeah.
this is very speculative, but according to what the simulations they have together, you need both an extreme wind and you need a low density CGM. The low density is very low density. It's within the realm of feasibility, but it's not typical. So I think you need both a unique galaxy and a unique CGM, and that combination might explain why we aren't seeing more. I realize that might not be, that's my best guess. I don't have a better answer to that for now.
Okay, thank you. So let's move to the next speaker, or let's come again to Alison. She's going to talk about the extreme transformation in the local universe, the radio.
come here. It's a lot of fun. It's a great place. But it's especially wonderful to be here for Paul. I can't believe how many people are crammed into this schedule, how many people wanted to come and talk. I certainly did. And my place in sort of Paul's pantheon of people is that I'm one of the earliest people to work with Paul. I'm probably the first person he mentored. He was still a postdoc at the time, and I was a graduate student at Berkeley, and he was a Miller Fellow. So our interactions are probably a little different from many of you because we were more, almost at the same level. He's a little older, and also Sara Beck when she joined, and so there was this give and take that was great. Another piece of context was that this was in the early 80s, and there weren't all that many women in astronomy in the U.S. Our numbers were beginning to increase, and it wasn't always the friendliest environment. But there were a few people who were good, and Paul was one. Okay. I'm not going to say any more because I'll get choked up. This is a list in chronological order of the people who worked on the projects. In fact, I think the particular source that I'm going to focus on, this is the list of people who worked on it, sort of chronological order, starting with the early 80s, mid 80s, and then Dave Meyer, et cetera, is the 2000s, late 90s and 2000s, back up to the present day at the end. So, a fair number of people working on this particular source I'm going to talk about today. Okay, so I've already gone into this a little bit, but this was a project. Jack Walsh was my thesis advisor. He had a great project for me, which was W30H. It was a 2-element interferometer at Hack Creek that I was using. It took a long time to get data. So I was looking for a side project. VLA was new. So Paul came to me with an idea. And there were a lot of postdocs there with ideas that were interesting. But Paul, I remember that first meeting sitting in his office. And he explained this idea, and he went for about 5 minutes, and I was totally on board. I said, this is a great idea. He kept arguing for about 20 minutes. I was already convinced. But what he said was, let's look at galactic centers that have mid-infrared emission, because there was this great paper by Ricci and Lobotsky in 1979. They must have radio emission. Okay, and he has said in the past, infrared astronomy is voodoo astronomy, but you can see he didn't really need it, because this was his argument for doing it on the great infrared emission. So here's our proposal. This is a duplicate copy. I still have it. Paul hates that I keep all this stuff. But the main thing here, the important thing here, NGC 253, IC 342, NGC 2403, and NGC 6946. Okay, so here are the reviews. I saw the reviews. We got the time. We did pretty well. But it was really interesting, the response, and you'll never see a response like this again. Reviewing today is not like this. Our top review said, okay, this is our top score, came from Ref D. He gave us a 0, which was top priority. My comment here is the same as for another proposal. We know little about the nuclei of galaxies. This is a totally new direction, the radio effort, potentially very interesting if positive results are obtained, which in my opinion is very unlikely, but it definitely deserves VLA time. So what referee is going to recommend giving time to a proposal where they think it's probably not going to show me? It's just not going to happen anymore. And it did here. It was great. So all of these comments were really good. This one hit it too. Do they need both 1.3 and 2 centimeters? Exactly right. 1.3 centimeter receiver was really very, very noisy. So the data weren't useful at all.
13 hours. There are 13 hours on those galaxies and logging Stevens' reception.
Yeah, no, I mean, it was a different instrument. It was new. Here are the results. So we did indeed, we got the first maps of this. The picture of the spiral galaxy at the time was that all star formation took place in outer parts, and the inner part was just like an elliptical galaxy, red and dead. And in fact, at the time, I showed the proposal to a professor in the department who should know, and he told me it was a stupid idea. So it's so much for a stupid idea. There are young people in the audience, take that into account. They say it's stupid, trust your own instincts. In this case, I was trusting Paul. Okay. So I thought this was great stuff. So I continued. W3OH was very rewarding too, but I really liked the galaxy thing. So did Sara Beck. She was working in the talents group, and like me, she was sort of a renegade because they tended to work on things in the galaxy, and she wanted to do other galaxies. So there's similarities. Paul brought us together. He was an assistant professor at Harvard at the time. She was an assistant professor at Northeastern, and I was a CFA fellow at the CFA. And we were using, so Sara brought us together to use the Beck spectrometer. She worked with Steve at Cornell, and we were doing the bracket lines at 2 and 4 microns. So one of the things we found was that extinctions are much higher than people were finding with the Balmer lines. So everyone was saying, extinctions in these regions are always 1 to 2. We know better than that because we do radio astronomy, but we found that, they were much higher. They could be up to 10 or so. Okay, so mine's on the move. We moved around. Sara ended up going to Tel Aviv. I ended up going to UCLA, and I have a couple of emails. There was no World Wide Web at this time, so this was the mid-'80s, but there was BitNet. So some of you may be old enough, very few, that remember BitNet. It worked with the ARPANET. There was an early internet, and it would tell you every computer it went through. So I would send a message to Paul and Sara at the same time, and it would get to Tel Aviv before it get to Harvard, because it depended on the computer line that you were willing to buy, and Harvard was too cheap to buy a long line. And so I had to go through every little college in New England. So that was, it was fun watching it. But anyway, here are the emails. We had fascinating exchanges, colorful. And one of the things about Paul, if he respected you, he would give you a rough comment. He would just mark up your papers and stuff, red ink all over the place, call you stupid. If he did that, it meant he respected you. Because he respected you enough to say, I think you're wrong, let's talk about it. He wasn't patronizing, he really took you serious. It was great. So, same message I just sent Sara. You two can phone in as much trouble as you want, but one more grenade lobbed in my direction, and I'm calling in the B-52s for an airstrike. I don't know what that was about. I don't remember arguing about this paper in particular. It says 1988. Try holding your breath and have the hospital call me. Where's the bracket paper? So, we've seen evidence of this. Where's the progress? Okay, so now I'm going to go on to talk about the current research, which is based on this galaxy that Sara came up with in the mid-'80s, and I've been obsessed with it ever since, and so this is something Paul values, which is persistence. So a little bit of history. It's kind of hard to see this galaxy, this picture of the galaxy. It's a little galaxy. It's a dwarf spheroidal, which means that its dynamics is dispersion dominated. It's like a little elliptical. Tiny little galaxy, 1% of the stellar mass of the galaxy. Blue compact dwarfs. It has this interesting dust lane here, and it has an incredible H2 region. So Burbage in 62 did a paper on H alpha, and they picked out 2 galaxies. One they showed an image of, which was M82. The second they showed a spectrum of, and it was this one. Oh, thank you. You can see it a little bit better. So it's got this interesting dust lane here. It's about 4 megaparsecs away, so it's pretty close. But it's kind of crazy. What we're doing in this galaxy today is trying to study star formation on the cluster scale. And why would you do it at 4 megaparsecs? Why not just do it in the galaxy? Well, I think when you see what this cluster is about, that might explain it. Okay, so here are the VLA maps. This is just to orient you, it's right at the very center of this. So it's a tiny little box in the center that we're seeing here. These are the radio maps that we got. Sara published this one in '96, I think. The 2 centimeters all free emission. This is 6 centimeter. There is a supernova remnant there. Most of it's thermal. So there's an incredible H2 region, but what it is 10 to the 9th solar luminosities within about an arc second, which is about 20 parsecs in this map, which is impressive. Yeah, kind of easy. So what was this incredibly bright radio source? Now this is an argument you really had. Oh man, the bitmap was going back and forth on this one. Sara says, it is clearly an H2 region, end of story, I don't hear anymore. Paul says, it's an AGN. And I said, well, it could be anything. I was going to go on with that, it could be a bright supernova. This was for a VLA proposal. And I won't show you that, so we did get nice images from the VLA proposal. It did not settle the story at all, but gave us better maps. But I will show you the highest resolution map we have from the VLA, which was made with Python. So this thing is really far south. It's minus 30 degrees. And so this is the VLA image. In the background, you can see the H1 image. This is Lopez Sanchez. And you can see H1 is a little asymmetric. So there's something interesting going on with this galaxy. In the background here, you can see this area here. This box corresponds to this. This is from Daniela Calzetti. And this is the overlay on the HST MICMOS image. What really was gratifying to me as a radio astronomer was that the VLA image made the HST image look blurry. Isn't that great? Okay, so, and we put it here. I had a huge argument with Daniela Calzetti, who was convinced that this thing here, this blue source, so this is the 1.9 micron source, which is the embedded source, the cluster. She was convinced this was it. We had this argument. I think it's finally been settled. It is the embedded source. So what does the gas look like? This is an Owens Valley map that I made. Again, it's pretty far south of Owens Valley. This is CO1 to 0, and this is the emission. And you can see this. Here's the nebulas right here, and here's the CO. CO extends along the minor axis, and this is a tiny galaxy. Most of the CO is not in the galaxy, it's outside the galaxy, and it's falling in. And how do we know it's falling in? We can see a projection, we can see the dust lane, and it's redshifted. So we know the direction of motion is falling in. This has been claimed to be an outflow, but people were using the H1 as a systemic velocity, and this galaxy is very dangerous. You saw that tidal tail, or whatever it is, going off to the side. But this is infalling. Okay? This is my favorite image of CO. We also did 2 to 1 because Nick Scoville said, this is one of the ugliest maps I've ever seen. And so they gave us more time to do 1 millimeter, which is crazy. And we still saw this. So it just confirmed it falling in. So this is the SMA image, which is a beautiful image. It's actually prettier than the ALMA image. And this cloud was a total surprise. We did not expect to detect this. And all of a sudden it comes booming up. This ratio is actually higher than allowed by Rayleigh Jeans for a single component. It suggests 300 Kelvin, but really CO3 to 2 cannot trace this gas, too hot and bright. And this streamer, this infalling streamer, has 3 to 4 million solar masses falling in, and you can see it right along the dust lane. So this is the cloud associated with the cluster. This is the ALMA image. Now ALMA, you can see it doesn't get the streamers. This is very undersampled, especially in the streamer. But it's useful for isolating the central cloud. So here is that cluster right here, the VLA center. I've overlaid the VLA 6 centimeter image with this. You can see the radio continuum lines up nicely with the CO, which is the red here, that almost CO3 to 2. But let's look at the very center. So let's see, do I have a scale on this? 1 arc second, so this is 1 arc second, here's about 18 parsecs. Okay, so this is very tiny. This thing has a radius of about 2.5 parsecs, has 1,000 O stars within that radius, and it has this bright cloud. And we believe this CO is mixed in with the cluster. So if we want to study the formation of a superstar cluster, something that is, 500,000 solar masses, this is the way to do it. Think about it, 500,000 solar masses within 2 parsecs. This is the cloud that's doing it. So the CO is coincident in projection with this cluster, with the radio continuum source. The velocity centroids agree to within 2 kilometers per second. So it agrees in velocity, and finally it has unusually weak 13 CO. So these are 3 pieces of evidence that yes, indeed, this is a cloud directly associated with that cluster. So here it is. You can see the 13 CO. In this cloud is not associated with the cluster. It's off about 15 parsecs away. Kind of interesting, but not directly involved. And if you compare the 13 CO, this 12 CO, this 13 CO, you see how weak it is. So the cluster is effective gas. The other clouds are, not too different from Orion. The ratio of 12 CO, 13 CO. Flux. And finally, the line profile. So this is another bit of information. This side of the line profile is affected by that cloud to the right. This thing is a little redshifted, so it has a little filament that seems to be coming over here. You can't see it in this map, but it is visible. And so that's affected. This is why this looks lumpy, but look how smooth this looks. It's a smooth line, and it's very close to Gaussian, so it suggests that there are many clumps. Many clumps to get a nice smooth Gaussian line. If you look at the signal to noise on each one of these channels, it's really high enough to tell us. So I modeled it with hundreds of clumps, and they're protostellar disks that might be fewer. The CO gas is not being blown out, so it could continue to accrete. And the dynamical mass, which we get, which is about 300,000 to 400,000 solar masses, combined with the infrared, with the radio luminosity that we see, we can't fit a normal ion map. There's no way. Now I need to try new stellar models. I tried every model in Starburst 90 and I couldn't do it. So this is a very interesting source. We're pursuing it. These are just a list of the conclusions. So we continue. We are expecting all the data. This is the 3rd time around for band 10. We've gotten approved 3 times, but the pandemic came, and then there's TAC came, and there's weather. So I'm hoping to get CO76 to see exactly how hot this is. And we also have JWST data on this too, the full mid-infrared spectrum. So, only a couple more slides. Why is this interesting? The models for gas dynamics of Silage and Torrio suggest that sufficiently massive and compact clusters could enhance by enrichment the cooling so much that they can stall winds and even supernovae. It's certainly consistent with the CO profile we see. We do see things leaking out, but it's individual little H2 regions there. They haven't merged. Wolf-Rayet stars, I should point out, there are probably Wolf-Rayet stars here, lose 60 to 75% of their initial mass, and they're massive stars. So a 100 solar mass star will lose 70 solar masses in enriched material, and it's 10 times solar. So this is going into the cluster. So imagine what these clouds are. They're super solar metallicity. This could explain why the cluster appears to be dusty and a way for the early universe to enrich. It's not a surprise that the early universe appears dusty. because Wolf-Rayet stars, unlike AGB stars, emerge very rapidly. And if you look at a bright star from a galaxy, you are looking preferentially at O stars that are emerging. Okay, but Paul could still be right. There could be a black hole in the center of this thing, and there is still potential gas accreting. There is that streamer that is still falling in. If it continues to fall in, and it can, then it could form. What could it form? What is the gas going to form? So the future of this source is really intriguing. Okay, so it's been the best while. I thank you for giving me a start in this wonderful field, and it's not over yet, so we still have work to do. So thank you.
We should move to the next. Then any questions, please find Jean in the coffee break. And now let's move to the next talk by Sara Beck. The title is Embedded Proto-Star Clusters and History.
There is going to be a certain amount of overlap between my talk and Jean's. This is going to be kind of like Rashomon, we're getting two different viewpoints. But I think you'll see that they're taking a different view and different take on things. First of all, I did not come up with the cluster in 5253. It was created, it was there. Okay, it wasn't my invention. It's true I've been obsessed with it since 1979, but that's a different problem. I'll explain that later. So this is the history of talking about embedded proto-star clusters in general. I say it's a history both of how we came to find them and of how the star clusters themselves seem to evolve. And something I want to emphasize is that this is a case where the observations had to lead the theory. There was never a theory that said, you will see embedded proto-star clusters, they will look like this. We stumbled on them, and we were the first. We, in this case, is me and Jean and Paul. We were the first. And observations lead theory, and the instruments lead the observations. You can see how the resolution increased, how we went to higher resolution. We didn't quite go to a factor of 1,000 higher, but 500 higher spectral resolution. That's what improved our theories time and again. And how do you drive this thing? Okay, good. So, mid-1980s, I remind you of the state of play. Paul had a paper called High Resolution Radio Observations. That was the title of the paper. It was 10 arc seconds. The VLA had come online in 1980. Infrared, 6 or 7 arc seconds was the best we could do. But the world of infrared had gotten a big kick with the 1984 IRAS mission, which followed on the Bobsky-Enrique's paper and said, there's enormous infrared fluxes coming from galaxies, and we think it's star formation. So we set out to observe these galaxies, the radio. This is the, oh, sorry. Yeah. Okay. On the light. There. This was that 2-centimeter map, very high resolution, 2 arc seconds at a time. This was the best kind of rapid spectra you could do in 1990. Took several hours on the best telescope of the time, and the beam again was around 500 parsecs. Not great resolution. But even with this mediocre spatial resolution, we came up with 2 important scientific results. One is that the star formation was extremely spatially concentrated. We could recover in our 6 or 7 arc second beam half or 80%, or in some cases all, of the IRAS flux in a 40 arc second beam. And the second was this radio suppression, that the bracket lines, the recombination lines we observed with the Cornell spectrometer were too strong for the radio continuum. Any graduate student knows that you get the ionized gas, the radio continuum does the same thing as recombination lines. How can you suppress the radio continuum? So, sorry, we jibbered over this for a bit, trying to understand this weird radio spectrum. This is what Jean referred to as the picture of the 3 monkeys. I really cannot put my hands on this. This was the point at which at one point we had a line in a paper, draft of a paper, saying we are of 3 minds about this source. We do not agree on it. I wanted to quote like a tree in which there are 3 blackbirds related to the poem 13 Ways of Looking at a Blackbird. I mean, the Gene of Paul, I'd never heard of it, so I couldn't quote it. But we established, finally, I think, agreed that at least the good working model was that just as in our galaxy, we will see optically thick radio emission, suppressed radio emission, very strong infrared nebulae around individual OB stars in an early stage of their formation. Compact H2 regions are called ultra-compact H2 regions, that we were seeing the giant counterparts of these, where instead of one OB star, we had thousands of OB stars at a very early age of development. So we were looking at the cluster analogies of ultra-compact H2 regions. Armed with this observational criteria, we went out and found over the years a population of these deeply embedded, up to at least 50 magnitudes, gas-rich, young, massive clusters. They're bound, they're massive, they're probably protoglobular clusters. Like our globular clusters were 12 billion years ago. So now, what is interesting about finding massive bound clusters? I'm going to talk a little bit now about the history of a star cluster. Molecular cloud, star formation starts. Every parcel of gas in that molecular cloud is going to go one of 2 paths. There's one of 2 channels. Gravitationally collapse to be a star, or to be expelled from the cloud. Because star formation is a violent process. All yesterday afternoon, we were watching jets, outflows, winds. It never stops. Stars are trying to get rid of the gas around them from the moment they're born, even before they're born, protostars. At the same time, gravitational collapse keeps going on. Which path dominates? And again, I go the wrong way. If you have low star formation efficiency, a slow collapse, stars are kind of forming amp, the gas will be dispersed, you will not be able to form a bound cluster, the stars will eventually disperse. This is all of the young massive star clusters in the Milky Way have this very low star formation efficiency. They are not going to be bound clusters. To get a high star formation efficiency, rapid collapse, really efficient, everybody turns into a star before it can be dispersed, you need a low virial theorem, a low virial parameter, high formation, star formation efficiency. How do you get this very high efficient rate of collapse? The average giant molecular cloud, like in our galaxy, is just about virially supported by turbulence. It's not going to collapse efficiently. You want to get the cloud to collapse properly, you have to overpressure it, smack it with something. Here we see molecular clouds colliding, and that's where you see the star clusters forming. That's from Sophia. It's been known statistically since the days of IRyA that if you have collisions, interactions, or mergers in galaxies, you enhance the star formation because you're increasing the pressure. And now now let's look at exactly how that happens. What we see when we look at these star clusters forming is that specifically, you can see the bound clusters forming where we have accreting filaments overpressuring the giant molecular clouds. I'd like to show you one extremely nice example of this. This was with Jean and Michelle Consiglio in 2018, I think. Here you see in the color, the red is an alpha map of CO3 to 2 with about 0.3 arc seconds. The white and blue are the near infrared. These are star clusters, individual stars in a galaxy around 10.5 megaparsecs away. And if you say this looks like star formation in a filament hub, you're absolutely right. But unlike the filament hubs in our galaxy, this has many millions of stars involved, just much bigger. Here we see the velocity field of that CO. I draw your attention to this one cluster here. You cannot see it in the near infrared, it's too obscured, but it's a very bright infrared source. Here's the CO filament tracing a dust lane onto it. Here's the velocity. Here's the channel map. As you go down the filament from here to here, you go in velocity getting redder and redder. It is being slammed down onto that filament at around 30 kilometers a second. So here we have the accreting filament, an extremely bound cloud, variable parameter about 0.8. Here's your example of efficient star formation. And now we go back to 5253, and I quite like the ALMA map, maybe better than Jean does. This is Michelle Consilio's map. Again, here's a streamer, the red. Here's another filament on this side. Here is the cloud D. This is the Calzetti map that shows the ages of the star clusters in megayears as you go through this jewel box of star formation. This is the very youngest one up here. And I would never get, maybe this is the right direction. And this is another view of that cluster that Jean was talking about. You see it's lying in the very obscure region. Okay? This is the most massive and compact cluster we know, over 1,000 obese stars and no optical emission. We're very lucky to have it so close to us that we can study it. Here we see, this is a recent map published. This is with Paul, Jean, Bo, you, a couple of other people. The black contours is showing the radio continuum of the JVLA. This is the highest resolution radio map that doesn't use Python. The color shows the CO cloud, and as Jean said, we are seeing this cluster still completely immersed in molecular gas. It has strong ionized gas, strong radio emission, but also is completely immersed in its cocoon. Or perhaps each individual star is still immersed in its individual cocoon. This is a very special stage in the evolution of the star cluster. We are very lucky to be able to see it so close to us. And we also have something I mentioned, we're talking about less, because it is the infrared, and we all know Paul thinks about the infrared. With John Lacey's TEXI spectrometer, very high resolution kinematics, we're studying the kinematics of the ionized gas. You see that we have these leakages coming out here and here. Here we have the velocity field at very high resolution. This is the line profile of every point across this map. Again, trying to figure out exactly how the gas is going to get out. Because two big questions in the evolution of a cluster like this: what gets it started, and where is it going to go? And again, I never get done the right direction. Okay. So I just covered what gets it started very, very, very quickly. I think that we are looking at the picture of infall gas, streamers, filaments coming in, disturbing molecular clouds, and starting to collapse. Now, where do they go? OB stars are violent. You have a lot of OB stars that are going to be trying to get out. So here is an example of emergence of negative feedback clearing out the gas. Here we have Ionized Q10 again, the two clouds, very different conditions. In this case, the white contours show the CO and the color shows radio continuum. This is a high velocity, 4 kilometer a second resolution spectrum of the ionized gas at 12.8 microns. This side obviously has got less molecular gas, less obscuration. It's on its way out. It's got some high velocity wings. This is not continuum. This is going out to 700 kilometers a second. This guy, this is the one that still has the cloud falling down on it. Much narrower, symmetric, virialized. The gas is still tightly bound. The gas is not yet starting to escape. We're watching the two stages. One of the big questions and trying to work on is how do we link up from this to this, where the gas is escaping at 50 to 100 kilometers a second, to eventually to the great cluster winds we see, especially in starburst galaxies, in several hundred kilometers a second. And again, the wrong time. Okay. Now, as Jean was saying, not every cluster is going to be able to clear out the gas. This is Stolen, Chris McKee, and Crumholtz. If you're in this region of compactness, of mass and radius, none of the violent activity of OB stars, including even supernovae, will be sufficient to get rid of the gas. What happens in that case, finally I do it the right way, is that, as Silas, Taylor, and their co-workers have demonstrated, you can have a situation in which the winds of the stars will collide, shock, cool, they cannot escape, they sink back into the cluster, and you have multiple generations of star formation. And this sort of shows, in terms of mass and radius compactness, the region in which you will develop a cluster ring, the region in which you won't. Many of our old friends are sitting here in the region in which you will not develop that cluster ring. This obviously needs more work. We need much more work. Shopping list of all the observations we need to do, of all the theoretical work we want to do. Paul, there's a lot of stuff we need to keep on doing. Thank you.
Thank you very much. We have room for one question.
The question I'm interested in is, how important is the far infrared for you? You're talking here about the JWC and ALMA for the next set of observations. How important is it for you that we get an interferometer in far infrared?
I think it's very important because now, I don't have much personal experience in the far infrared, so I'm kind of in a vicious circle here. I'm saying we don't know enough about the dust. The dust is a big, big question. There shouldn't even be dust in gas that hot, and yet there is. What the heck's going on there? You know, how is it existing even, let alone what is it called, what is it made of? So I say this is a place where I think I know I need much more information there. So yeah, that is a big, big gap. That's an honest answer. I say we need more. And we still have a big gap in spatial resolution between the radio and the infrared are now dealing with about the same spatial resolution, but the far infrared are not so much. So we need that.
Thank you very much. So now we have a coffee break, but just one comment. Lourdes Garden in Montenegro will be able to talk. So we are going to move the first magnetic fields and star formation talks. So I have Hawaii, Kaohsiung, and Johnson. So we prepare because we will have to move 50 minutes ahead. Thank you very much.
So now we have coffee break, right? We got
Now we have a coffee break.
by 11. Yeah, we come back by 11.